Hello everyone, welcome back to another video, and today we're going to be talking about prime factorization. Prime factorization is used in a lot of problems in many different ways, so I'm going to show you how to use prime factorization effectively in many problems. But first we're going to be talking about last week's homework problem, which is about grid walking. So if you want to skip this and go to prime factorization, to this timestamp. Okay, so I told you last week that you can use two methods, and the first method is much simpler than the second one, but takes a while. So I'm just going to put the solution on screen. So here's the solution using method 1 from last week. And you can see it gives you the answer of 38. But now let's discuss the much faster solution of method 2. So we're going to use a technique called complementary counting with method 2, where basically you find the number of ways to go across A and B without the restriction. So let's pretend this line is connected. So we can do that. And then you subtract the number of ways to get from A to B that use this line that's not supposed to be there. And that's called complementary counting. So first let's find the total number of ways. We see that this is a 5 by 3 grid. So using method 2 from last time, we can arrange 5 R's and 3 ups in 8 choose 3 ways, which is just 56. And now let's see the number of ways to go across this line, which should not be there. So we know to go across this line, we need to start from this point over here and then go to this point over here. So how many ways are there to go from A to this point over here? Then we can cross the line that should not be there and then go from the other side of the line to B. And that's how many ways there are to go across this line from A to B. So first let's see how many ways there are to get to A to the leftmost point. So it's a 2 by 2 grid, so that's just 4 choose 2 or 6. And then the rest of the journey from the right point to B, well, that's a 2 by 1 grid, so that's 3 choose 2, and this is just equal to 3. And now since it's an AND situation, like we can go to A to this leftmost point, and then for each of those we can go from this rightmost point to B, we're going to have to multiply these two together. So 6 times 3, which is equal to 18. And now we can use a complementary counting step, where we do 56, which is the total number of ways, minus the ways that are forbidden, and this gives our answer of 38, which is the ways which we can go. And this is the same answer as we got using method 1. However, we can see this is much faster than method 1, and with practice you can see how to do this quickly and become way faster. So this is the solution to last video's homework problem. So let's take a number, find its prime factorization, and then I can show you all the tricks that we can do with the prime factorization. So let's just take a guinea pig of a number, like 144, very nice number. And this is just equal to 12 squared. 12 is equal to 2 squared times 3, so this whole squared. And this is just equal to 2 to the power 4 times 3 squared. So the prime factorization of 144 is 2 to the power 4 times 3 squared. So now let's see what we can do with this. The first thing you can do is find how many divisors, so number of divisors, 144 has, which can be very useful. And this is just equal to this and this exponent plus 1, and then you multiply them together. So 4 plus 1 times 2 plus 1, which is equal to 5 times 3, or 15. So we know 144 has 15 divisors. And what's the reason for this? Well, we know any divisor of 144 is going to be in the form 2 to the power of something times 3 to the power of something, because those are the only prime numbers that divide 144. And we also know n is going to be less than or equal to 4 and greater than or equal to 0. And then the same thing for 3, just with 2. So m is less than or equal to 2 and greater than or equal to 0. So let's see, how many choices are there for n? Well, that's 5 choices. And how many choices are there for m? 3 choices. And for each value of n, we can pick 3 choices of m. So this is just 5 times 3, which is equal to 15. And this is what we got here. And you see here, this is just 4 plus 1 times 2 plus 1. Another thing you can do really simply with prime factorization is GCD and LCM. So if you have two numbers, 18 and 42, and we find a prime factorization, so 2 times 3 squared, and then 2 times 3 times 7. The way you find GCD is you take each of these primes, and let's just say this is 7 to the power of 0, and you see the least exponent. So for 2, the least exponent is going to be 1, since they're both 2 to the power of 1. For 3, it's going to be 3 to the power of 1. And then for 7, it's going to be 7 to the power of 0. and this is just equal to 6. And now for LCM, you do the exact opposite and you find the greatest of them. So 2 to the power of 1 times 3 squared times 7 to the power of 1. And this is just equal to 126. And one cool thing, if you take the LCM and GCD of two numbers, the product of the two numbers is actually equal to the product of the GCD and LCM. So 6 times 126. And if you check this, it all checks out. And the reason for this is because one of the powers is the least and one of the powers is going to be the most. So that's just going to be the product of the two powers. But mind you, it only works for if you have the GCD and LCM of two numbers. You can also use prime factorization to find the GCD and LCM of multiple numbers, more than two. So if you have three numbers like 12, 18, and 22, find the prime factorizations. So 2 squared times 3, 2 times 3 squared, 2 times 11. The GCD would be the least, so 2 to the power of 1 times 3 to the power of 0 times 11 to the power of 0. And then the LCM would be the most, so 2 squared times 3 squared times 11 to the power of 1. And if you calculate these out, you get the GCD is 2, and the LCM is going to be equal to 396. And how simple that was. It took maybe 15 seconds if you don't talk, and it's a very quick way of using prime factorization to find GCD and LCM. Now let's say if you have a factorial like 12 factorial, and you want to find how many powers of 2 are in there, so 2 to the power of what? And to do this, first note that 12 factorial is 1 times 2 times 3, all the way till 12. So every other number will have a power of 2 in there, because 2, 4, 6, 8, they all have powers of 2 in them. So there will be 6 even numbers in here, because 12 divided by 2, and each of these contributes 1 power. So far we are up to 6 powers of 2. But remember, there's also going to be powers of 4 in here, and we need to count those twice, so we want to count those once more. And the number of powers of 4 is just 12 divided by 4, or 3. And remember, there's also going to be powers of 8 in here, and the number of that, it's 12 divided by 8, 1 point something, but you can just ignore the rest and just say 1. And this means there are going to be 10 powers of 2 in here, so to the power of 10. So what we're doing here is we're counting how many numbers have a power of 2 in them, how many have a power of 4 in them, and then how many power of 8 in them, and we can just continue this. So let's say we want to find how many factors of 3 are in 100 factorial, which is really big, right? Well, we can just use this. So how many numbers are divisible by 3? Well, that's just 100 divided by 3, and then the lower bound of that. So 100 divided by 3, 33. And then how many powers of 9 are going to be in there? It's going to be 100 divided by 9, or 11. How many powers of 27 are there? Well, 3. And then how many powers of 81? Just 1. And if we add this all up, we get 47. So 100 factorial is divisible by 3 to the power of 47. And this is how to find how many powers of some prime are in factorial really quickly. So now let's apply what we learned into a problem. So let's say we have 10 factorial, and we want to find how many divisors it has that are not divisible by 8. So let's first find the prime factorization of 10 factorial, which is now really simple using our last method. So how many factors of 2 does it have? 5 plus 2 plus 1, or 8. 3 to the power of 4, because 3 plus 1. 5 squared times 7. And I just did this a little fast, but you can go through each of these primes and use the same method I just showed you a few seconds ago. And now we want to find how many of these divisors are not divisible by 8. Well, we know 8 is 2 cubed. So our number can only be divisible by 2 to the power of 0, 2 to the power of 1, or 2 squared. It can't have any factor of 2 bigger than 3. So there's 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. 3 possibilities for the factor of 2. And then for 3, it's 0 through 4, so 5. For 5, it's 0 to 2, or 3, and then 2 for 7, 0 or 1. And this is going to be equal to 3 times 5 times 3 times 2, or 90. And look how quick this is. It would have taken so long. We would have probably had to list all of the factors, which there's a lot of, but now we can just use simple multiplication to find there's 90 divisors of 10 factorial, not divisible by 8. So today we learned about prime factorization, which is very common and has many different uses in many problems. So we learned how to find the number of divisors of a number using prime factorization. We also found how to find the LCM and GCD of many numbers very quickly. We found how many powers of a specific prime are in factorials, and then we also learned how to combine all of these together and deal with restrictions. So I hope you enjoyed this video. Thanks for sticking around all the way till the end, and I'll see you in the next video, which is coming up in a few days. So stay tuned for that.